Today I will continue solving project Euler. I believe we will still have some not very interesting problems. Some people suggested me to solve recent problems. Moreover, like 8 hours ago, a recent problem appeared. This one. No. Maybe recursive tree? Maybe recursive tree, I'm not sure. Where is it said? Not account, maybe news? Yeah, news. So the next recent problem will appear. Oh, 4 a.m. Oh my god. So the next problem will appear in 7 days. But unfortunately, so the today problem appeared 10 p.m. I can say yesterday because it was on 13th of January. However, I felt not very well. I felt very sleepy, so I had to skip it. So I still don't have any recent problem solved. Let's go with this problem. We need to find the index of the first term in the Fibonacci sequence to contain 1000 digits. Well, actually, this is the first time where I apply my brain. So there are like two ways. First way is just to calculate all of these Fibonacci numbers till I get 1000 digits. And the second way is to apply Binet formula.
Binet.
Binet, I don't know. I'm not sure. It says Binet. Russian we say formula Binet. So to apply it, we just need like, let me turn on my whiteboard. Okay, so I have a whiteboard. Fibonacci sequence is a particular partial case of a common thing called linear recurrence. So what's so interesting about linear recurrences is that while this equation is linear, the growth of this number is usually exponential. Moreover, you can even find the exact formula. Maybe the exact Euler formula is what is called Binet formula. Well, Binet is French person, so I think it's Binet. So how to find this formula? I believe what we say is we state that we believe that the solution looks like the following. We say that it's definitely Fn equals sum of ai to the power of n times ci, where ai and ci are some complex numbers. So we just say we believe that it should be of this form. Yeah? After that, notice that since this equation is linear, what do I mean by linear? So if you have two sequences which agree with this definition, then their sum also satisfies it. So f plus g is also, it is also true that it is of this form. Moreover, okay, you will see later what I would like to say. So f plus g, so like what I want to say is, if we consider set of all possible answers to this linear recurrence, then it is closed under usual linear operations such as uh, taking sum of two numbers or multiplying some sequence by alpha, where alpha is any complex number. So you can as well multiply this equation, this equality, by some number, and it still holds. So you're interested in the set of all possible sequences, and since this space is linear, you just want to find a basis. And it's natural to consider such numbers as a basis because, firstly, they are linearly independent. So it's easy to see that you cannot have several different such sequences because such that their sum is zero. So you cannot have zero as the sum of such sequence unless all CIs are zeros. The reason is because if you consider the maximum AI by modulus, it will grow faster than anything else. So if you consider A as the biggest number with non-zero C, it should be sum of minus sum of all the others AI to power n times Ci. And this grows, oh, n, sorry, here is n. And this grows faster than this. You just need to consider two cases when A is positive and A is negative, but it's not hard. You see that it grows faster. Therefore, so first of all these sequences of this form are linearly independent, even of this form. But the second thing is they are generating. And why they are generating, I'm not sure how to prove it strictly. Moreover, it's not true because of multiple roots. I will explain later what is the set of needed solutions here which generate all possible sequences. But for now, we will assume that we found some sequence A to the power of n, which is the solution to this Fibonacci sequence. So A to the power n plus 2 equals n to the power n plus 1 plus A to the power n. Then you can divide it by A to the power n, and you get the following equation, which is quadratic. You can solve it using discriminant. So A equals 1 plus minus square root of 1 plus 4 over 2. So this number, 1 plus square root of 5 over 2, is called phi. And this number, which is the second root, is called minus phi inverse, I believe. Okay, so now when we know all the principal solutions of this recurrence, how do we find the coefficient Ci? Actually, to do that, we need to consider the, I think it's called initial conditions. So we know that f0 is 0, and it is c first times phi, c first times phi to the power of 0, plus c second times minus phi inverse to the power of 0. Yeah, because we know that both roots of this equation, where the left side is called, it's called characteristic polynomial of this recurrence. So we know the both roots of our characteristic polynomial, and we try to raise them to the power 0 and to the power 1. Also, you can use here, instead of inverse, you can use here what? You can say that it is simply 1 minus phi. Yeah? Yeah, I believe it's 1 minus phi. Yeah, because of the Viet's or Viet's theorem, I think it should be Viet. This sum is one of these two roots. Okay, so c first times phi to the power of to the first power plus c2 times 1 minus phi to the first power. Okay, and now you can clearly see that this means that c1 plus c2 is 0. So let's say that c2 is minus c1. And this thing says that c1 times phi plus minus c1 times 1 minus phi equals 1. Then you just solve this equation. You see that c1 times phi minus 1 plus phi equals 1, and easily c1 is 1 over what? Over 2 phi minus 1. So 2 phi minus 1 is easy to see. It's easy to see that it is equal to square root of 5. So it's inverse square root of 5. That's how you get the final formula, which is phi equals, oh no, not phi, but phi, fn. Fn is equal to phi to the power of n minus phi to the power minus n over square root of 5. Okay, why am I interested in this formula? In this particular problem, I'm interested in the first moment that this number is at least 1000 digits long. That is, it is at least 10 to the power 999. Yeah? Yes. But notice that this number phi is greater than 1. This means that this number is less than 1. It's actually less than 1 by absolute value, but it is negative. So minus phi, I mean, if you take minus phi inverse, so it is in from minus 1 to 0. This means that this thing exponentially goes to 0. It is an exponentially small number. That means that actually this is really near this number. This is really near phi n over square root of 5. Yeah, because the second addend is really small. It usually doesn't matter at all. Okay, so you want to find the minimum number n such that this number is at least 10 to the power 999. Then we can take logarithm of this inequality and you get the following. N logarithms of phi minus logarithm of square root of 5 is at least 999 times logarithm of 10. And this is a linear inequality, and you get that n should be at least this number. Nice. What we can do here is we can just check that these two ways agree and find starting at which moment they agree. So starting at which moment this is really a small enough number to not be accounted for. We will write two solutions. First of all, I'd like to create a temporary project, not temporary project, but temporary file. And I want to do that so that I could simply copy this file instead of copying the last file I have. So I read something. Okay, let's do it with one input. Usually it will be just one input. Okay. So what do we do here? Let's copy it. Let's create a project. And let's use a target library for this project because I would like to have long arithmetic here. Finally, I need this input file, and in this input file, I only use one number 1000. So I want to print actually two answers here. I want find answer binary and find answer GMP. There will be two ways of doing it. And we will compare them on smaller ends and on the final end, which is 1000. So to calculate binary, we simply ignore the second term because it goes to 0 exponentially fast. So we just solve this inequality, and this is kind of easy. So we need to take n minus 1 times logarithm of 10. Let's use LD as long double. However, on my platform, which is Visual C++, you don't have long double. Unfortunately, you have only double. I think you can maybe even see that. No, you can't. But still, long double is same as double. Maybe you can find it as this. Yeah, see, instead of finding double logarithm, it just finds a usual double logarithm. That's because Visual Studio doesn't want me to have high precision in such problems. This is unfortunate. Okay. So n minus 1 times logarithm of 10 plus logarithm of square root of 5 divided by square root of 5. No. Logarithm of phi. Of phi, which is, I think, phi can be even defined in math constants. Yeah, let's see. Do we have phi? No, we have logarithm of 10, but I believe we don't have phi. Okay, let's use it. After all. So here we can replace it with logarithm of 10. And here we use, so logarithm of 5 is, square root of 5 is this number. Here we take its logarithm, and here we take logarithm of 1 plus square root of 5 over 2. Okay, and we take its ceiling, and we return it. Okay, this was bine. Then let's work with GMP. How do we work with GMP? So it's kind of easy. We have NPC class. First of all, it has just Fibonacci function. We will not use it because we will need to calculate a lot of Fibonacci numbers. If we only had to calculate one of them, then there is an optimized function which does it. Yeah? But it does it with, what's called? It does it with binary exponentiation, I think. Yeah? It's simply binary exponentiation, which is kinda binary exponentiation for finding this phi to n, but it does it exactly, not with an error, because it uses integer matrices instead of long double. Okay, but I don't use it. I don't need it. Instead, I simply do it in linear time. So the reason why this method is somewhat better, it is worse because it won't work for little n, because we cannot actually simply ignore this addend. For little n, this addend is somewhat big. For big N, it can be ignored, and thus this method is kinda exact. You will still get the wrong answer when n is really large, because you don't have enough precision of this number and of this number. This will surely lead that at some point the answer will be incorrect. Okay, MPC class M. Okay, A equals 0 and B equals 1. And we store the number of B, let's call it B number, which is 1. Is it 1? Oh, this is not a very good notation. So when you use, so it should start with, no, it's great notation, sorry. F0 is 0, F1 is 1, so this is fine. luckily project Euler is led by mathematicians. Okay, so while b dot str get str dot size is less than n, we do the following. First of all, we say that we want the following. We want a b to become b and a plus b. To do that, you can say that a plus equals b and then swap a and b. Anyway, a dot swap. We can a dot swap b. Okay, now this is it, and after that we need to say plus plus bn. Okay, in the end, if b get str dot size is n, we can return bn. However, if for some reason it jumped over this length, which it couldn't, we return -1, or even let's throw something. Throw runtime error. Great. Now let's check it for 1000, that it gives the same number both times. Oh no. I ran the other file and I didn't change these input files. Let's see if the answer is same. Yes, the answer is same. Let's check if it is same for 1, for example, because I believe it can be not. No, it's same. And for 2? Okay, for some reason, this term didn't mess it up. For 0, I believe it will throw the exception. Because I used the same function for some reason. I should have used here GNP. Now it will throw an exception, definitely. Yes, it threw. Okay, let's check again for 1. Okay, see, now actually GMP says that the answer is 1, and it is correct. But the long double function says that it is 2. This is not correct. Let's check the answer for 2. Yes, it is fine. For 3, it is fine. And for 1000, it is also fine. So there are 2 solutions, with or without long arbitrary precision arithmetic. Let's go on to 6. A unit fraction contains 1 in the numerator. The decimal representation of the unit fractions with denominators 2 to 10 are given. While this means 1/6 and has 1-digit recurrence cycle, it can be seen that 1/7 has a 6-digit recurrence cycle. Find the value of d less than 1000 for which 1 over d contains the longest recurrence cycle in its decimal fraction part. Okay, this is a theoretical problem. To do that, you need to understand what it takes for the number to have for the rational number to have some recurring part. Actually, when you divide a number by another number, at some moment you will get only zeros after the decimal point. And this means that this process is somewhat cyclic. Yeah? How do you divide it? By hand. You have some residue. you add 1 0, then you divide it by number b, so it should be some b's. You subtract these two numbers, you get some new residue. So you have Rn, and here you have Rn plus 1. Then you add one new 0, subtract something, and have Rn plus 2. So on. It's easy to prove that this sequence Rn, it is cyclic. You can, so if you have two equal residues, then the next residue will also be the same. These two numbers are equal. Moreover, it is easy to prove that actually it is backwards. The same works backwards. So if you have two same residues, and they got from some Rn and Rm by this operation of adding 1 0 and subtracting something, then these two numbers are also equal. So it always looks like the following. You have some pre-period, and then you have some period. So it is a periodic sequence, and you know that the moment you have at least one such 0, it is definitely in the cycle. Great. I mean, I think. Okay, not exactly. Not exactly, because actually this only works if Rn is divisible by all 5s and 2s in B. So since the moment when, so first of all, you need the moment when you only have zeros here, and secondly, you need the moment when v2 of Rn is at least v2 of B, and v5 of Rn is at least v2 of B. I think when you have both of these, then you can definitely say that it is purely periodic. You can, at this moment, you can definitely say that if you don't have any more digits from number A, then you're definitely in the cycle. Okay, but how to solve the problem? To solve the problem, we need to find out how can we fastly find the length of this period. Actually, you know in this case that Rn is simply 10 to the power of n mod B. So you need to find the first moment when these two residues are the same. So you need the moment when 10 power of n modules B is 10 to the power of m mod B. And for that you need two things. First of all, let's consider B as the product of two numbers, k and p, where k is 2 to the power of so many 2's as there are in B, and 5 is the product of, and as many 5's as there are in B also. And p is b over k. So k is the maximum integer divisible by only 2's and 5's, such that p has unit GCD with 10. Okay, when we have done it, that by Chinese remainder theorem, we can say that it is equivalent to 10 to the n being equivalent to 10 to the m modulo k, and it should be equal modulo p. and then the length of the period will be the minimum possible m minus n. Okay. The first thing is simply, it firstly states that, okay, also we can say that n is not equal to m. It's easy to see that if you don't have v2 2's here and v5 2's here, yeah, so n is less than either of these numbers, then this equality can't hold, because this integer k keeps track of any 2's and 5's if there are no more than this number of them. So it can discriminate between all these cases. So if you have, for example, k equals 500, so v2 equals 2 and v5 equals 3. So unless you have, if you have at least 2 2's and at least 3 5's, it will be 0. This residue is 0 of this number. But if at least one of them is less than the corresponding power, then you will get a non-zero residue. And all these residues will be different. So if you want these things to be equal, you need to, actually, let's say that n is less than m for the sake of completeness. So what I want to say is that it says that n should be at least maximum of v2 of b and v5 of b. That's it. This is what it says. Okay, this says that simply 10 to the power m minus n should be 1 modulo p. So actually, if we want to minimize this number, we are not interested in this condition. This condition simply holds if we take both numbers big enough. So this doesn't say anything about the difference of m and n. It only says something about n and m themselves as big enough numbers. So we want to find the minimum possible m minus n such that this is 1 modulo p. Actually, there is a name for this number. It's called the order, the multiplicative order of 10 in the group ZP star. So ZP is a group of residues modulo p by addition. But ZP prime, ZP star is group of, how it's called, residues modulo p such that they are relatively prime, and this works by multiplication. So you need to find the minimum number k such that 10 to the power of k, sorry, k is reserved L, such that 10 to the power of L is 1 modulo p. When you find it, it's called discrete logarithm as well. So if you find it, this is your answer. This is the length of your cyclic part. So to find the length of the cycle, you need to find the order of 10 modulo your number. Moreover, you don't actually need any numbers except, so you don't need 2's and 5's. If you use 2's and 5's, you still go into this condition, because the only thing that 2's and 5's add to your condition is this thing, which doesn't affect m minus n. Okay, to solve this problem, To solve this problem, we need to go through all numbers from what? From 2 to less than n. We want to find the length of the cycle. So first of all, if I is divisible by 2 or it is divisible by 5, we continue. Let's assume that they are not divisible by these numbers. Then we need to find the order. So we calculate the order of 10 modulo I, and if O is greater than max O, then we say that max O equals O and answer equals I. And here we store max O, which is 0, and ans equals 0. And we return the answer. Let's write the function order. To do that, we want to, first of all, we take b% equals p, and int residue, current residue, it is b, and current order is 1. While r is greater than 1, is not 1. You do the following. You replace r with r times b modulo p and plus plus o. And in the end, you return o. Great. Finally, we create a new input file. And here we store 1000. Let's see what it says. It says 983. I think this is because okay, let's just print the order of this number, of 10 modulo this number. I believe it will be just 982. So we say that, yeah, 982. In this case, we say that 10 is a primitive root modulo 983. Okay, let's go on. Euler discovered the remarkable quadratic formula. Turns out that the formula will produce 40 primes for the consecutive integer values of this segment. However, when n equals 40, it is not a prime. Okay, let's consider quadratics of this form. Find the product of coefficients a and b that produces the maximum number of primes for consecutive values of n starting with 0. Okay, since this formula is incredible and it was discovered, and it has b greater than 1000, it is easy to see that it is unlikely that we will have much more than 80. So I'm actually interested if there are some fast ways. I have come up with not a fast way. We simply we have n squared plus an plus b, it should be prime for n at least 0. So first of all, if I take n equals 0, this is simply b. And if n equals 1, it is simply 1 plus a plus b. Okay? So I want to consider all pairs of primes with difference at most 999. I subtract them. So I get b and a. Actually, no. Actually, I don't. So a may be negative. So I take just two primes p and q. Then I say that b equals p and a equals what? Equals q minus p minus 1. So since I want these two numbers to be at most 1000 by absolute value, this means that b should be just any prime from 1 to 1000. And a should be, here q should be taken accordingly. So q should be from 1 to 2000. 2001. Okay, I consider them. Then I just check the primality easily. Okay, to do that, let's use Eratosthenes sieve, which I believe is in the 7th problem. Yeah, maybe it's also in the 10th problem. Yeah, it is in the 10th problem. Okay. Not Eratosthenes, but Eratosthenes. Eratosthenes. Okay, and I just check these two numbers and I return the nice answer. I definitely don't need long arithmetic, so I don't turn it on. I don't believe it will be big. I think it's at most like 100 terms or 200 terms, but not like thousands. So here we only have n. Let's... Okay, project is created, so I put 27 here and 27 here. Let's just, to not mess with the upcoming files, I will put here 2 zeros at period. So, find answer. Okay, first of all, we need to find all primes. So let's take 10th file, copy this. Eratosthenes. And it will return pair of vector ints. How does it work? So we will return primes and min divisor. This is not interesting. This is not interesting. Here we return primes and min divisor. Nice. So here we return them for something like 3n squared. Or 4, even 4n squared. should be written like this. Then we want to iterate over all primes. So this will be B. And here we say that if B is greater than n, we break. Okay, then I want to consider A. How do I consider A? I ask, is it true that I just say that for int q in primes, I say that A is B q minus B minus 1. So if A is so if this doesn't hold, then it does not hold either from the left part or from the right part. So there are two cases. This can be at most minus n, and in this case I simply continue. But it's also possible that if A is at least n, then I need to break. Now I have A and B, and I know that this polynomial, it is indeed prime for n equals 0 and n equals 1. So let's store best A equals 0, best B equals 0, and number of primes. Best number of primes, which is also 0. In the end, I will need to return absolute value. Not absolute value, but simply the value of A times B. Best A times best B. And before that, I would like to see them. I would like to see them. Let's see them. So let's store number NOP, which is now 2, because we have n equals 0 and n equals 1. And 4, I think we can rewrite it like this. Nope equals 2. Nope. I don't know what, but no plus plus. So we would like to check here that if we substitute nope here, it is still a prime number. How do we do it? Let's write a function is prime here, and we are done. Finally, if nope is bigger than best nope, we replace best A with A, best B with B, and best nope with nope. Let's now write the function is prime, which will use our Eratosthenes sieve. How does it do it? First of all, it checks that if P is at most like 3, return P is at least 2. This is easy. You don't want any negative numbers. If P is at least mean divisor, then we will throw an exception, which will say 2 small Eratosthenes. Otherwise, we simply return that return that mean divisor of p is simply p. Mean divisor of dot size. And semicolon. Oh, we are done. Let's check our solution. To check it, we need to give it 1000. It's already there. -124? I don't think so. -124? What? Ah, it should be not prime knob, but it should be known is prime knob times knob plus a times knob plus b. Here it is. Okay, and how many numbers? 71 numbers. Okay. Okay, great. We go on. Starting with the number 1 and moving to the right in a clockwise direction by a 5 by 5 spiral. A 5 by 5 spiral is formed as follows. It can be verified that the sum of the numbers on the diagonals is 101. What is the sum of the numbers on the diagonals in a bigger spiral? So again, we clearly can find the answer by some pencil and paper. It is possible. However, I will not. I will simply implement this function and see where it goes. Or no. No, let's not construct all this spiral. Let's only look at these numbers, because I feel like I'm too lazy. I feel like I'm too lazy to do it by hand, like write the whole function. So let's turn on our brain for a little bit. So if we have some beginning number, then no matter what the size of the spiral is, of the square, we definitely know that, for example, this is number 3. It is always 3, and it is always 13, etc. So we just need to find what kind of sequence is this, 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 and this, and we are fine. We can even go further to have a O of 1 solution, but we will not. We will actually only have linear solution. Find answer. It seems like it might be long. So how to do that? We simply ask about 4 sums. Like we have 1. So if n is at most 1, we at most 0, we return 0. Otherwise, we return 1 plus something. So like find upper right answer of what? So let's also consider what is the okay, it only makes sense for an odd n, so we have odd n. Let's only consider odd n, and in this case In this case, it always ends here. So we can as well just say that find upper right n over 2 plus find upper left n over 2 plus find down right of n over 2 plus find down left or of n over 2. So we need 4 formulae. Moreover, I think I will just use a cycle here. So I equals 0. Okay, let's choose 1. I is at most n over 2 plus I. And we ask for arms plus equals this thing, where it is I. And we need only 4 functions. Okay, so let's start with this one, going here. So it's easy to see that these are just squares, and it's odd squares. So we need to find ith odd square starting with 9. It's easy to see that it is simply 2i plus 1 squared. So return 2 times n plus 1 times 2 times n plus 1. Okay, lower left should be down left should be also easy because it is always almost squares. It's like squares plus 1. Yeah, because this is always a square. Because this is always a lower point of this 4 by 4 square. And we take the next number, which is square plus 1. So we need here 2n times 2n plus 1, which is 4nn plus 1. Okay, we have 2 more, which is down right and upper left. Okay, let's start with down right. Hey, how do we find this number, for example, or this number? This number is simply the size of this rectangle and plus 1. What is the size of this rectangle? The size of this rectangle by y-axis is I believe it's simply 2y minus 1, 2n minus 1. Okay, 2n minus 1. And the x size is 2n, isn't it? N plus 1. And finally, upper left, it can be also found, and it is the size of this rectangle plus 1. Okay, what is the size of this rectangle? This rectangle by x-axis is simply 2n plus 1, and by y-axis it is 2n. Fine, let's see what it says to us. Let's start with the easier one, which is 5. Okay, so the file is changed. This should be changed. and we see that it is 101. Yes, so all our formulae are fine, and now we write 1000. We have this huge number. I'm surprised that it is still less than int. So we can simply write this answer. So we have somewhat linear solution. Problem 29. Consider all integer combinations like this. They are then placed in numerical order. And we want to find how many distinct terms are there in the sequence generated as a to the power of b. Again, there is a way to apply brain and a way to not do it. The way without applying brain is simply putting everything in an ordered map. Do we want to simply put it in an unordered map? Okay. I now see one more way, which is hashing. So if we have two numbers a and b, we can simply calculate a to the power of b modulo some modulus. And if the modulus is big enough, we won't get any collisions. And if we don't get any collisions, then our answer is correct. However, the collisions are definitely possible. Okay, let's just do it. Modulus some modulus. Because I don't want to use long arithmetic here. 29, 29. 29. 29. Okay, we're at n, we find ans n. So what do? We go through all numbers from a and b. So the simplest thing would be to calculate it modular. Okay, let's use two different moduli. So we have like set of pair of int and int. P. And in the end we return, no, not P, but S. We return S dot size. Here we simply return so int ans equals 1, while b, we say that if b and 1 ans, let's also write a function product of int a and int b in some modulus. We return long a times b percent p. Okay, answer. If b is odd, we replace answer with product of answer and a modulo p. And if b is at least 1, at least 2, we multiply a by a. In the end, we return answer. Great, we now need some set. And here we say that s dot insert, let's also store two primes. Two primes, and here we insert power mod of a b p and power mod of a b q. And to not have any problems with inserting two numbers, what? It is incorrect, we should use in place. Fine, let's target this target. 9183. So what if we use two equal primes? Will it get any incorrect answers? Yes, actually there are possible collisions. Unfortunately. Okay, let's use tuple. Int. And let's use one more prime. Because I somewhat don't like it. So it's 83. What if we use 11? Actually, this is not a prime number. It is divisible by 3. But it doesn't matter, actually. Okay, 2 primes is enough. 2 primes seems enough. Okay, problem 30. Surprisingly, there are only 3 numbers which can be written as the sum of the 4 powers of their digits. I would include 1. It is a sum. We find the sum of all the numbers that can be written as the sum of the 5th powers of their digits. Actually, I'd like to say the following. So let's write some inequalities. So let's fix the number k equals 5. Then we want some number an, a1, etc. an, which is equal to a1 to the power of k plus a2 to the power of k, etc. plus an to the power of k. Notice that it is at most n times 9 to the power of k. And this is at least 10 to the power of n minus 1. So definitely, if we want this equality to hold, we need this thing. So we need 10 to the power n minus 1 over n to be at most 9 to the power k. For instance, if we take k equals 4, we get that... What is 81 squared? I actually forgot what is 81 squared. It is 729 times 9. Let's multiply it by hand. Yes, obviously. So it should be at most 10 to the power n minus 1 over n. And if we take n equals 5, it is actually okay. Still, there are no numbers of length 5 at all. but still. So we can actually iterate until something like this. So this is a solution which works in O of like k times 9 to the power of k time, something like this. We just iterate until this number and we find their number. Let's write this solution. So find answer n, and that's it. So let's replace it with k. Let's write a function which is good, which takes a number n and a number k. And it checks that n is the sum of the kth powers of n. How does it do it? So we say while, let's also write like int power of int a int b, which is something like power mod. We have int ans is 1, while b, if b and 1 ans times equals a, and if b is divisible by 2, after dividing by 2 it is still small, it is still big enough. We multiply a by a, finally we return answer. While n, we say that sum plus equals int power of n% 10 and k, and n is divided by 10. We return sum. Also, let's write the find answer. How do we find the answer? So we iterate. First of all, we need to find this bound. We can find this bound by a linear search. So for int n equals like 10 and n equals 1. So we want it to be, so let's assume that this is n is 10 to the power of n. We want to check whether we want to increase n or not. So how do we do it? Let's assume that we increased n. So now we have 10 to the power of n over n plus 1. It is still at most 9 to the power k. Let's check it. So while n divided by n plus 1 is at most 9 to the power k, and we can as well calculate this power. While it is at most k, we increase n and multiply n by 10. Okay, now we know 10 to the power of n, and we can simply check all the good numbers. We start with 2 because 1 is for... Actually, we start with 10 because everything else is forbidden. And if good of I... we need to find the sum of all these numbers. Sum plus equals I, and we return sum. Let's check our solution. First of all, we need to Create a new target. We need to switch to this target. We need to rename our files, and we need to create a new file which stores number 4. For now it's 4. Let's look at the answer to that. We need I and K. Actually, I'd like to have two different functions. Sum of powers. So here I return sum actually. And good is a boolean which returns that n is equal to sum of powers of m and k. It says that it is 19,316, and this is correct. Now let's look at the fifth thing. Yes. For the sake of our interest, let's print it. There are 6 numbers like this, and even there is at least one number with length 6 or length 5. Great. So we can return the answer, and it is a correct answer. Problem 31. In the United Kingdom, the currency is pound and pence. Isn't penny like the singular of pence? There are 8 coins in general circulation. Yeah. It is possible to make 2 pounds in the following way. How many different ways can 2 pounds be made using any number of coins? Okay, this is a standard knapsack problem. No, I shouldn't duplicate 13 file. I need to duplicate this file. Okay, let's solve this problem about pennies. What pence? 31, 31, 31, and 31. Yes, so how is it done? First of all, 2 pounds we will represent as 200 because it is 200 pence. To solve this problem, we will find a DP which consists of n plus 1 numbers, which is the number of ways to represent this value. Okay, so also we have several coins. Yes, we have several coins. We have a tuple size. Then I think we can write it like this. Int coins constant coins equals what it equals 1 to 5, 10, 20, 50, 100, 200. Yeah, now we have this DP. which calculates how many ways. So first of all, when this dp is calculated, it is calculated for some prefix of this array. For example, in the beginning, it is calculated in the empty prefix of this array, so we can't use any coins. dp says what is the number of ways to produce this number using no coins. And the answer is the characteristic function of 1. So if the needed amount is 0, then there is 1 way. And if the needed amount is positive, then there are 0 ways. Now we will increase this prefix one by one by iterating a coin in coins. Can we do it? It seems like we can. It seems that it can. So let's assume that we are looking at some coin. Then we can add one or more coins to the answer. Let's consider that our answer is increasing list is the list of all used coins in increasing order. So now the coin is the maximum possible coin in our arsenal. Can I say like this? Yeah. In our weaponry. So if it is added, it is always added in the end. So always, if you have some dpi, you can increase dpi plus coin by. So each of these ways contributes to one more way of these ways. So it can be rewritten as for int I equals 0, I is at most n minus coin, dpi plus coin plus equals dpi, and finally return dp n. Let's see how it works. It works pretty well, I think. Yes. 32. We shall say that an n-digit number is pan-digital if it makes use of all the digits from 1 to n exactly once. The product 7254 is unusual as the identity. As this identity has 3 numbers which are pan-digital is in total. Find the sum of all products whose multiplicand multiplier product identity can be written as 1 to 9 pan-digital. Some products can be obtained in more than one way, so be sure to only include it once in your sum. Okay. Okay. So, how is it done? Let's again repeat the whole process. Actually, don't like this problem. I don't even think that we need any input here. It seems that it is a non-parameterized problem. It is parameterized by the number of digits in our system, but I don't want such a parameterization. Okay, so we don't read anything, we just print the answer. How do we do it? We need to iterate over all undigital numbers. Hmm. So how many, let's think about how many digits can be in these two numbers. Okay, so in the first number, there can be 1 or 4 or 3, 1, 2, 3, 4, 5 digits. Easy to see that it can be 6. Here also we have 1, 2, 3, 4, 5, 6. 6 is impossible, no. We will not use 6. So let's see how many digits are there in the product. So actually, if you multiply two numbers, the number of digits is either sum of the numbers or sum minus 1. So it can be 1 or 2, 2 or 3, 3 or 4, 4 or 5, 5 or 6, 2 or 3, 3 or 4, 4 or 5, 5 or 6, 6 or 7, 3 or 4, 4 or 5. Also, we can only consider cases where this number is at least this number, then we don't need this part. We're not interested in it. So 5 or 6, 6 or 7, 7 or 8, 7 or 8, 8 or 9, 9 or 10. Now we can easily see that we don't need the most of this table. We only need a short stripe somewhere here. So, for example, it is allowed to have 4, 5, and 1. It is also allowed to have 3, 5, and 2. And I believe that's it. Yes, that's it. We cannot have anything else. Only 1, 4, 5 or 2, 3, 5. Yeah, this is because if we have A digits here and B digits here, then here we have A plus B or A plus B minus 1 digits. So the total number, actually we need 9, so no. 2, 3, need 9. So since we need 9, it is easy to see that we need this option. Yeah, because if we use this option, then the total number of digits is even. So we need A plus B plus A plus B minus 1 is 9. This means that A plus B is 4. This means that we have... What? 5. Sorry, 5. So this means that we either have this option... What? A plus B equals 5. It's either this one or this one. I see. So we are only interested in 4-digit products. Okay, so let's do it somehow. We iterate over all 4-digit numbers. And we need to find the sum of these numbers. So we need to... Okay, it should be... int should be enough. So let's write something like if good of I, then sum plus equals I. Let's find good bool or bool good. So to do that, let's make some vector of booleans of size 10. and int used digits equals 0. So we wanted to get to the 9. So let's say that it should be 9. And we return that it is 9. First of all, we need to check all digits which are in n itself. So to do that, say, let's iterate over. So we say that int temp equals n, while temp, we say that if v temp% 10 is already used, we immediately return false. Actually, let's write it as a function. Auto process int temp while temp, if this, then we return false. Otherwise, we say that vtemp%10 is true, temp% equals divided equals 10, and plus plus used digits. So we need to process it. So after that, we need to check that we have at least one number from 1 to 199 such that it forms a good triple with n. So how do we do it? We simply say that how do we do that? We say simply that, actually, let's make it a function. Let's say bool process. It has integer int temp. It has a reference to an integer used digits, and finally it has a vector of bools. And here it says return true. Here it says return true. So here we ask that if you failed to process n, then return false immediately. N, used digits, and v. Now we iterate over all numbers. So if actually we say here that if it is good for n, I, v, and used digits, then we return true. Else we return false. Okay, let's now make this new function bool good of n, a, and these two things. What's wrong? Here I use actually this with copy. So I need to firstly check that n is divisible by a. Then I need to process a. What? Okay. And I need to process b. Otherwise, I return use digits is 9. Finally, I need to switch to new file. I need to write it here. I need to run it. Okay, something like this. Let's write all such triples. I want to look at them. So I want to see, for example, 7,254. Okay, we see it. Yeah. Okay. Okay. What? Ah, I need to check it. So if there is a 0 digit, I should ignore it. Yeah, for example, you can see here that if you have 0, it says that it is still fine, but it is not. So in a function process, actually instead of changing function process, I can simply say that v0 is true. I can even say that 1 and 10 here. This, no, I don't like it. So let's just write like this. And now it should be much smaller, and we have only these 7 equalities. Now it works. The fraction, this fraction is a curious fraction, as an inexperienced mathematician in attempting to simplify it may incorrectly believe that this is 4 over 8 by canceling these 9s, but actually this is a true equality. Fractions like this are trivial examples. There are exactly 4 non-trivial examples of this type of fraction, less than 1 in value and containing 2 digits in the numerator and denominator. If the product of these 4 fractions is given in its lowest common terms, find the value of the denominator. Okay, I need to multiply these 4 fractions. This is kinda... So, the... How it's called? Let me remember one word. Okay, this is called phenomenon. The phenomenon is kinda interesting, but the problem itself is not. Because you simply iterate over all possible 2-digit numbers and check something. Oh, fine, let's write it. We need some GCD, which is while b a% equals b and swap ab. Find ans also is unparameterized. So we again don't need to use any input file. I'll still use it, although not read anything. Great. Now we can say here that I want this. And I want this. How to do it? So let's iterate over all possible numbers. Let's start with numerator. It's easy to see that you simply need the numerator to not be divisible by 10. It is enough. First of all, if, let's do it like in a nested way. So if numerator %10, then we iterate over denominator. Also, there is a trivial example, less than 1 in values, 1 in value. So we start with numerator plus 1. Then we need to check that there is a common digit in them and you can remove it. So how to check for a common digit? So let's say that n1 is numerator divided by 10 and n2 is numerator %10. Okay, and here we also say that there is a d1 and d2, which are denominators. Actually, it should be 0 here. Yes. Okay, now we need to check that. Find the intersection of these two sets. Like int inter is 0. If d1 equals n1 or d1 equals n2, then inter is d1. Else if d1 equals d2 d0 equals n1 or d0 equals n0, then inter equals d0. Okay, else inter equals 0 and I remove the initialization. So if inter, then I try to check that numerator times d0 plus d1 minus intersection equals denominator times n0 plus n1 minus intersection. And if it is true, then these two fractions are equal, and I need to add it to the answer. Let's write a function which adds something to the answer. How it is done? How is it done? So we need to find the product of these four fractions in its lowest common terms. So we need to say that ans n equals times equals n, ans d times equals d, int g equals gcd of ans n and ans d, ans n divided by g, ans d is divided by g. Okay, and we simply add numerator and denominator. Also, I'd like to look at this fraction. Great. And finally we return. What do we return? We return the denominator. And let's print everything. Okay, there are indeed 4 fractions. Nice ones. And the product is 100. Wow, it's incredible. Who would think? Who would imagine something like this? Problem 34. 145 is a curious number as it is equal to the sum of factorials of its digits. Find the sum of all numbers which are equal to the sum of the factorial of their digits. Let's again start with analysis. So we have some number and it should be equal to the sum of factorials of its digits. And actually this, so let's write it again like this. And this is at most 9 factorial times times n, and this is at least 10 to the power n minus 1. So if we want this inequality to hold, we want this, and since we want this, we want to 9 factorial be at least 10 to the power n minus 1 over n. And this again is done by the same procedure as we already did. It was in beginning, I don't remember. I don't remember. Ah, here it is. So this is what we need in the 30th problem. We will use this function because it calculates the same thing. 4, 4. It is again non-parameterized problem. So again, the input file is empty. We create it just in case. And let's do it. We don't read anything. So let's start with the function of factorial. And we need the factorial of 9. Okay, then we need to find such maximum n that 9 factorial is at least this number. This can be done. Actually, let's pre-calculate all factorials. Let's pre-calculate all factorials. We say that fi equals fi minus 1 times I. So actually we don't need this function. This is redundant. And now we say that it is simply f9. And don't want this constant now. So let's use this procedure, which finds the minimum such power of n that this is at most this. Actually, so I want this to be at least this. So actually I want to divide with ceiling. Since I want to divide with ceiling, I need to write it like this. Okay, here I simply put f9 here. Yeah. Let's write it as a function. So int no, I don't want to write it as a function. Not interested. Great. Now we have the power of 10. Now we can iterate over all numbers which are at most which are less than n. Let's calculate everything. So we say sum of factorials is 0, then while temp sum of factorials plus equals f of temp percent 10. Actually, we skip 1 and 2, so we start with 3. Actually, we start with 10 again. Then what? Then temp is set to be divided by 10. Yeah, and now if sum of factorials is I, then let's print actually and add it to the answer. Let's look at them. So there were not many of them, only 2 of them. Okay, this is kinda a lonely set of numbers. "35. The number 197 is called a circular prime because its rotations are themselves prime. How many circular primes are there below 1 million?" Okay, first of all, we need to use Eratosthenes sieve as always. This is finally a problem with an input which is 1 million. And we want to create a new project. So how do we create the project? How do we implement it? So we need to check all numbers. Let's just do it. Let's write a function which iterates over all numbers from 1 to n, and it checks. Let's make a structure which checks. and we create a structure. We initialize it with number n. We need to find the sum of all. How many? So if number I is a circular prime, we add 1 to CNT and we return CNT. Let's construct the circular. How do we do it? And we need bool circ int n const. Let's make other function is prime, which is kind of trivial. Let's find Eratosthenes sieve. I don't remember where it was. 29th. Where was the sieve? Here it is. Let's copy it. Pum, 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 pum. Okay. So how do we check that the number is prime? We need to take Eratosthenes, which we will store in our structure. We simply check that if n is at most, we return n is at least 2 and return. Okay, if n is at least mean divisor dot size, we return false. We throw. And finally, we return mean divisor of n equals n. No, it is prime, which is also const function. How do we check that the number is circular? First of all, we need to find all its digits. Instead of finding all its digits, we will find the number of the digits. Number of digits, which is 0. While temp is divided by 10 and plus plus number of digits. Okay, now we know the number of digits. Then we need to check that all the circular numbers are prime. So for int I equals 0, I less than not, plus plus I. So we need to check that. Also, let's find the power of 2 corresponding power of 10. Power of 10 times equals 10. And let's divide it by 10. So this is the power of 10, which corresponds to the leftmost digit of n. Yeah. So we want to check that. Is it true that... Okay, let's again say that temp is n. So if temp is not prime, we return. Otherwise, we replace temp with temp divided by 10 plus last digit times power of 10. Okay, and we return true. Yeah. Finally, we need to run this circular thing, and to do that, we need to find the minimum power of 10, which is at least n. When we have done it, we need to store it in errata things. Of pot. Can I do it? Okay, can I do it like this? Is it possible? Wow, it worked. Since it worked, I enjoy this because this means that C++ is not the worst language possible. Okay, since I've implemented it, let's look at the answer. No, I didn't run the correct file. $55. Let's look at them, maybe. Let's maybe look at them. Let's maybe look at them. It seems legit. Okay, I believe. I believe it. So we take 55 and print it. Extraordinary. Let's solve the last problem and I will go to have some rest. This decimal number is palindromic in both bases. Find the sum of all numbers less than 1 million which are palindromic in base 10 and base 2. Okay, so first of all, since it should be palindromic in base 2, it should be odd because it cannot have leading zeros, but after reverting it, it would have leading zeros, which is not acceptable. So we only consider odd numbers, and this implies that it will be maybe palindromic in base 10. At least it will not have trailing zeros. Then, what do we do then? We simply check the palindromicity. I see. So I think we can iterate over all palindromic numbers, palindromic decimal numbers, and then check if they are palindromic in binary. Do I like it? Or not exactly? Yeah, I like it. Let's do it and have a rest. Let's go. So starting with creating the problem 36, 36, 36, 36, 36, and finally 36. 1 million, yeah. So we read it, we need to find the answer. So we start with int ans is 0, we return ans. To do it, we go through all numbers which are... How do I want to do it? How do I want to do it? Okay. Actually, hmm. Actually, I do the following thing. Instead of iterating over all, first of all, as Yegor Gorbachev, which I again go say hello, and Ivan Safonov, hello. As he said, it is not desirable to implement any like optimizations which are not needed. So this problem is easily solved in O of n log n time by just iterating over all possible numbers. However, I will solve it in square root of n log n time because it just makes sense. It just makes sense because this is how we work with palindromes. So if we have a palindrome, we actually don't iterate over all possible digits. It only iterates over first. So if we have a number of length k, we only iterate over this number of digits, k over 2 serine. This is because all these numbers are uniquely determined by these numbers, digits. So we don't need to iterate over them. Okay. So actually, let's start with 1. And what do I want to say? I want to say that I only iterate over this for first half. Now I need to construct two numbers. Is it below 1 million? Yeah, yes, less than 1 million. I look at the number. First of all, I want to just flip it. To do that, I say int a equals I, int temp equals I. Then I make the flips, so while temp, say that a equals 10 times a plus temp% 10, temp divided by 10, yes. So now I have a palindrome. Then I want to check, is it true that this number is less than n? So if it is less than n, I also need to check that it is binary palindrome. So if binary palindrome of a, then what do I do? I add it to the sum. I said ans plus equals a, and let's print it because it is interesting. However, this is not the ending because there are two problems. First of all, I still run in linear time, and secondly, I only consider even length palindromes. So to also consider odd length palindromes, I will start over, but this time I want to consider odd length palindrome, so I start with temp over 10. Then I do the same thing as usual. I have an odd palindrome, and if this time it is at least n, I break because this is too big number. If this is at least n, then I will never see at all any palindromes which are less than n. I will only see palindromes which are greater. So I stop. Okay, now I do the same thing. Not a. Yeah, a. Then I do the same thing. If a is less than n, which it is, and if binary palindrome of a, then I add it to the answer. Finally, we need to write the function binary palindrome. And to do it, I check that n equals binary reverse of n. Let's write now the function binary reverse. So while n, I say that answer plus equals n and 1, and n is divided by 2. No, answer is answer multiplied by 2 plus like what? I don't remember the... No, I remember that it should be like this. Yeah. Nice. Nice. This works. This should work. No, this didn't work. What about 585? So we should look at 58 here. It was never 58? What? What? Why didn't it stop? I should make the condition here. Okay. I should have done it here. Stopped it. Conditions a equals 58. Okay, now it works. Now I believe I should have a equals 585, and I need to check that it is a binary palindrome. I need to find its binary reverse. Okay. Of course, I should have done it like this. Okay, now we have a lot of various numbers, including 585. Okay, let's comment this thing. Comment this thing, and have some rest. Thank you for watching.